Okay there, welcome to Math 7, Unit 2, Lesson 12, using graphs to compare relationships. You began today's talking about some fraction multiplication and division, and you practiced doing some of those things mentally with some mental math there. Let's move on to today's first little activity where you had some kids that were walking or racing from the ticket booth to the bumper cars. And let's see what we have in this story here. First of all, we have three different tables down here to go with Diego, Lynn, and May's time and distance from the ticket booth to the bumper cars there. And the first thing it asks us to do is to take a look at each person to fill in the charts and then to translate that down into a graph here to talk about the differences and comparison things. So let's first of all take a look at Diego. It says that Diego left the ticket booth at the same time as Tyler, we don't know about. He jogged ahead at a steady pace and reached the bumper cars in 30 seconds. So he has a steady pace and he gets there in 50 seconds. So because it's steady, we could do find out what his constant proportionality is here. So 50 divided by 30 is 5/3. So we know he's traveling at 5/3 meters per second essentially. To find out how far that is at 15, I can multiply by 5/3 and come up with 25 like so. At 0, he's gone nowhere at all. That's where Diego has gone. So in terms of plotting this out for Diego, if I was to plot Diego out so far, we could say that at 15 seconds he has gone 25, so he's here, and at 30 seconds he has gone 50, which is here. Okay, this is Diego's distance so far, going 50 meters in 30 seconds is his ultimate time. So we put this here for Diego, and there is Diego. Put a D right there for Diego. One of the things you're going to notice as we go across here is because the ticket booth is 50 meters away, all of my lines are going to end up stopping right there because that's the distance they have to travel in total. It's a question of how long does it take them to get to that finish line right there. Okay, so now we take a look at Lynn next. And it says that Lynn's time here, she left ticket booth the same time as Tyler, and she also ran at a steady pace and arrived there in 20 seconds. So her rate is 50 over 20, or 5/2. 5/2. That 5/2 can also be written as 2.5, right? 2.5. That could work there to help us understand what her rate's going to be. And so to go this direction, remember we multiply by the reciprocal. So multiply by 2/5 instead of 5/2. So that becomes 50 over 5, which is 10. We notice a relationship here to here. This is cutting in half, so this is half as well. And so there is another relationship to take a look at. We also know that since she started at the same time, she had gone 0 meters in 0 seconds. We can add that point there. So for Lynn, we can drop her points in. At 10, she had gone 25, and at 20 seconds she had reached the goal of 50. So that's where she's at there for Lynn. We put an L, and let's connect our dots here between our dots and the origin because she started at 0, 0. So that's where Lynn is going to be. Now May was a little different here, okay? And so when I did this a couple times, I kept talking myself out of it. Don't do math early in the morning. Well, by early I probably mean like 4:30, too early. So when we looked at May, it says something different. It says she left the booth 10 seconds later than Tyler, and everyone else started, we know everyone started at 0, but she left over here at right this point. 10 seconds later is where she's going to begin her race, is down here. She's not starting at 0, 0. It says she has a steady jog, so we're going to have a straight line, and she's going to catch up at 50, 40. Okay? Now the thing here is that while she catches up at 50, 40, that point would be at 40 seconds she gets to her goal here. Okay, that's where she's at there. But let's draw this real quick as a line to see what's happening, because if we're going to reach this point and start there, we have a couple issues going on that it's helpful sometimes to draw the graph and see what's going on before I fill in the table. Oftentimes it's good at the table and then the graph. Sometimes if you're not sure, let's just take a look at what's happening here. So this is May. Here she is, and she's doing in her race, she's starting a little later, and she's arriving here in 40 seconds. She gets to 50 meters. That's where she's at. Okay. So she doesn't really have a constant proportionality. She is running a steady rate, so there is a number that it can get us there, but it's a little different because look at this. While it says it takes her 40 seconds to get there, in reality, it's only taking her 30 seconds. It's actually 40 minus 10 is how long it takes her to get to 50, right? So in terms of what's happening here, she's actually getting there at a rate of about, she's doing 50 meters in 30 seconds is her actual rate there, okay? She's not doing 50 and 40 because she started a little bit later. That's a key thing with this question, that it's easy to skip over that and not notice that, right? See, when she had gone in 10 seconds, after 10 seconds had gone, she'd actually gone 0 meters. And in 1 second, she had gone 0 meters. This number here is the one that's a little bit tricky. But let's see what it shows on our graph. It shows us that at 25 seconds, she's gone 25 meters. So we know this solution here is going to be 25. The question is, how do you get there? How do you get 25? And so what's happening is this. We know that typically our equations are going to be set up as y equals the constant proportionality times the next value. That's our basic equation there. But in this case here, we know that what's happening is our distance we know is 50. Let's take this one here. We have a 50. We said our constant proportionality is actually not 50, it's 5/3, isn't it? Right? So our constant proportionality is actually 5/3. Let's go ahead and change our 50 back to a y real quick, because he's traveling at a rate of 5/3, meaning we're going to go up 5 and over 3 as we continue along this journey. Now in terms of the x value is where it gets a little bit funny, because what we did with the x value is it's actually whatever the x is minus this 10-second delay. And that's what's taking place there again and again. So if we took a look at this one here, 25, to do this one to go opposite way, we would multiply by the reciprocal, which is 3/5, and that becomes 25 divided by 5 is 5, times 3 is 15. You say, well, 15 doesn't equal that. No, but 15 plus 10. Why plus 10? Well, here it's minus 10. I'm going the other way, so I'm going to do this plus 10 gets you to 25. So it's a little bit tricky to do this part here, right? But it does work out all right. Okay, so that's what May's graph is going to look like, and we plot those there. And it did say that Tyler started at 0, 0 and got there at the same time as May. So I can put a point here and start from the origin and get to May for how fast Tyler's going to run there to there. So there's Tyler getting there. Okay, so those are my 4 graphs there for how I get from one place to the other. Okay, a little bit tricky in some ways, at least the May one was, because starting a little later, that number might be a little tricky to find, but using the graph can help you get some pointers on how to get there. So which person is moving the fastest, and how can you tell? Well, the fastest is going to be which one has a steeper line or the steeper graph. The fastest person looks like Lynn, right? She's getting there basically in 20 seconds. She gets there, no problem, right? She's getting there in 20 seconds. Everyone else, Diego gets there in 30, Tyler's getting there in 40, and May, while it looks like 40, she's actually getting there in 30 as well. If you notice here, her slope looks the same as Diego's, doesn't it? Those two lines actually match. May and Diego have the same pace. She just started 10 seconds later. Okay? So that's what we had there. Now, in terms of are you ready for more writing equations, you could do that. If you work some equations down, Diego is going to be traveling at y equals 5/3 x. Okay, looking at our constant proportionality there. For Lynn, she's traveling at y equals 5/2 x. No problem there. We've already talked a little about May. Hers was a little bit more complicated, so that's a fun one to take a look at there, but y equals 5/3, and again, 5/3 because it's the same rate as Diego, same thing there, 5/3, but it's x minus 10. And that x minus 10 comes from that place right there, and that's what we have. Okay, let's take a look at the next one. So the next part you looked at, number 3, was space rocks and the price of rope. And it said that a meteor Perseid at 245 and asteroid X traveled through the solar system, and the graph shows the distance each traveled after a given point of time. And we want to know, is X traveling faster or slower than 245, and how do you know? Okay, and so the way we could look at this, a little bit like our last graph, if we plotted a distance, right, across a straight line, and it was a race, and that's the finish line there. If that's your finish line, then the time that you came in is going to be related to the X value down here, and the one that is getting to the finish line fastest is the one that has the steeper graph, the steeper line. And so we would say that asteroid X is traveling at a faster rate than 245 is going to be traveling, because it gets to the same distance in less time. Okay, so while you have two graphs, you can compare them by drawing some extra lines this way to see what's taking place, right? This might be, 10 hours, and this could be 20 hours, just making that up, for how long it takes to get from one place to the next. Okay, so, so using that information, we can also then look at things like different prices, and we can check to see how are prices different here. So this graph shows the price P in different lengths L of two types of rope. If you buy $1, that's the price here. If you just kind of rope, which one will be longer, and how do you know? So this is our cost on this side, and this is our length over here. Let's pretend this is 1, 2, 3, 4, just like that. Okay, just making up numbers. I don't have any idea. If I picked a $1 amount here and just drew a line, this became my point for cotton, my point for nylon, and we draw down. We say, well, for $1 I might get 1.5, but for nylon I'm going to get here 3 and a bit more. Alright, so in terms of the question being which one will be longer, I'm going to get more nylon for $1 than I will cotton, because I can see in terms of this proportional relationship how much extra nylon I'm going to get for that same price. So those values, you have to really read and think through, what is it saying? What is taking place here in terms of my length and my cost? And so I can definitely get more nylon in this case here. Okay, so here is your summary. It says here's a graph that shows the price of blueberries at 2 different stores. Which store has a better price? And so you have 2 stores and a better price, and we have A and we have B. One place you might want to start looking at initially is going to be down here at that K value, right? Our constant proportionality. This tells us how much these things are going to be. This is our cost in dollars and our cost in dollars. And so at store B, we have a cost in dollars of, it looks like, $4 per pound. It's for 1 pound. Or A, we're getting $6 for 1 pound. Okay, why? Because that's our constant, and that's our constant there. So in terms of which store has the better price, we would say, well, B has the better price because it's costing me $4 for a pound, and that one's costing me $6 for a pound. And so you can find that constant proportionality to help you determine the better value at different prices. Okay, we'll pause there and let's move on to your homework and go ahead and start that, and then come and check back in to see how you did. Alright, here we go. So looking at our homework for this evening, it says match each equation to its graph, and these are a little bit small to take a look at, so I'll zoom in a tad bit and see if it helps out a little bit. Okay, so this first one, we're going to see that we are going, and we have right here, we have our constant proportionality, which is what's happening from 0 to 0. This is talking about my ups and my downs and where I'm going. So we have this one, which seems to be going to this point right there, and so we notice that we are going, it's really hard to see today, a little less than 1, isn't it? A little less than 1 there? A little less than 1. So it looks like it's going up 1, 2, 3, 4, 5. So it's going up 4/5 of the way up, because there's 1 and 1 there. So my slope here is going to be 4/5 from what it looks like on number 1. Okay, that looks like a 4/5 there. Maybe it's easier to do something different. Maybe I need to match what I have. So that's a 4/5. So we can call this one B. That's my little slope there. This guy, here's my 1 value right there. Alright, there's my 1 value. So I can see that it's going 1, 2, 3. It's in thirds. So this is a 2/3 up to get to 1. So this looks like it's going to match choice D there. Here we have 1, 2, 3. So we're going by thirds. So I have 3. I have 1, 2, 3, and that's 4/3 there. I'm at 4. So this is a 4/3 slope. 4/3 to there. And so we have that guy right there. So we call that E. Okay. And then let's me back up a little bit, right? I'm working too hard. Silly me. All right, let's take a look at this guy. This guy goes at our point. Here's our point 1. Sorry, we're at 4, and then we're at 5. So that's easy B, all right? Here's a point. I'm not even seeing this point. It's just too early. Here's 2 and 3. So that's going to be D. Here we're at 4 and 3. So that's going to be E. Here we're at 1 and 4. So that's going to be C. Here we're at 4 and 2. So that's going to be 4 over 2, which reduces to 2. That's going to be A. And 6, we're at 3 and 2, which is F. Sorry about that. I was looking at the unit rate, which is true. That is our K value right here. This gives us our K value, but man, those are hard to see. And early in the morning, I'm just not doing well today. Sorry about that. So there's the faster way of doing it. Look at the other number. It's a little easier to see. Whoops. Luck number 2. Maybe this goes a little better for me. The graph below shows some data from a coffee shop menu. One of the graphs shows costs in dollars versus drink volume in ounces, and one of the graphs shows calories versus drink volume in ounces. So what we want to do first of all is asking us to label things. So we want to label these graphs and decide which one belongs to the dollars and which one belongs to the calorie amounts there, and give them the correct titles. Based upon what we see here, they all have ounces. You're probably not going to be spending $350 for 24 ounces of a drink unless that drink is super good, but it's probably not unless it's milk, so what can I say? So this probably here is going to be our cost in volume. This looks more like a dollar amount over here, and this over here is calories, because those are more calorie values there. You can see the calories are increasing by how much I'm drinking there. The second part, B, says which quantities appear to be in a proportional relationship. Okay, proportional relationship tends to mean it's going to be some sort of line there for how it's working. When I look at this one here, it's like it seems to be kind of curving that way. Okay, here there does seem to be some sort of line there. It doesn't quite line up the way I'd like it to be, but it seems to be more of a line. This one just seems to be a little more like it's curving to the down a little bit, but not down, but it's kind of decreasing its slope as we go around. It's hard to say. So I would think this one here looks to be a little bit more proportional, not tons, but it seems to be more proportional than the other one. Here again, the question is which one appears to be. Okay. For the proportional relationship, find the constant proportionality. What does that number mean? Okay, so constant proportionality means it's going to have the same rate all over the place. So let's see if this one has a constant proportionality. I'll take my 150, my y value, over my x value, which is 10, and I get 15. Okay, so if my constant proportionality is 15 ounces, or sorry, 15 calories, including calories per ounce there, sorry, 15 calories per ounce, because that's 150 calories and that's ounces. Does that work for this one here? 360 over 24. And when I do 360 divided by 24, 360 divided by 24 is 15. So indeed, this is a constant proportionality. My graph's not very great, but it does tell me that there should be a line that connects all these together, and that constant proportionality is 15 calories per 1 ounce is my constant proportionality for that graph right there. Okay, kind of interesting to take a look at there. So let's take a look at number 3. It says Lynn and Andre biked home from school at a steady pace. Lynn biked 1.5 kilometers and took her 5 minutes. Okay, so she is doing, so here's Lynn. So Lynn is doing 1.5 kilometers in 5 minutes. That's her rate there. And then it says that Andre biked 2 kilometers in 8 minutes. Okay, so in terms of their pace, their rate of what they're going there, 1.5 kilometers per minute becomes 0.3, or I could write, just for our sake here, 0.30 kilometers a minute. Okay, which means that after 1 minute he has gone 0.3 kilometers. Okay, there's our minute, there's our kilometers. For Andre, 2 over 8 becomes which is 1/4, becomes 0.25 kilometers a minute. So after 1 minute, he's gone 0.25 kilometers is how far he has gone. So after 1 minute, who's gone the furthest distance? Well, that'd be this one right here. Lynn has gone is going faster because she's gone further in less time. So to draw a graph there with our 2 lines, right, we could have our time be on the bottom. If we have our time be on the bottom, if we want to do that one there, or we can do the other way, time or the distance. We can go, yeah. So we can say time, and we can have 1, 2, 3, 4, 5, 6, and over here we can have our distance at 1 and 2. And so we know that after 1 minute, one person has gone a little bit. So after 5 minutes, 1, 2, 3, 4, 5, 5 minutes, it's gone 1.5, 6, 7, 8, and the other person after 8 minutes has gone 2, right there. So we have one graph here and one graph there. So it's not a great graph the way I drew this here, but you can see that they're going a little different rates. Make yours a little better than mine. Sorry about that. Anyways, have a good day. I probably should flip those around a little bit, thinking about it now. I probably want time to be here, and I should have flipped that around that way, but you get the idea. Anyways, good luck. See you next time.